So just really quickly, I really want to thank Stephen for inviting me, and thank all of you for your great talks and the great conversations that we've been having. These are two of my favorite little quotes about free will. I should add a third one. One of my toughest acts of free will is to stay awake after lunch. So I hope that you all will indulge me. I won't fault you for it if you don't. So I want to talk to you about what neuroscience can and cannot say, and has not said about free will in a more or less conclusive way. A fair part of my talk will focus on this thing that I have illustrated up here, which is something called the cortical readiness potential, which was long thought to be a signal or a signature that one is about to perform a voluntary movement. And I have the dominoes here falling down to illustrate at least the classical view of this thing, which was that it was a sort of the sign of a ballistic process that was hurtling towards you making a movement, a sort of commitment to initiating a move. And I'll talk about historically all of the different inferences and conclusions that were drawn based upon that, many of which I have shown may likely have been false. So first, a couple of my guiding principles, just in general as a scientist, but also as a scientist studying something like free will, which attaches great significance, which has a great significance attached to it. I think the first is humility as a scientist, to be keenly aware of what you don't know. And that's everything, right? There's very little that you know relative to what you don't know, even as a scientist. But at the same time, authority and confidence. And it would seem that those two don't go together, but they really do. And neither should be abused, right? But authority, sometimes you need to speak up from your scientific knowledge and say, yes, we know that, right? More often, though, the correction is, I can say with confidence and authority that we don't know that. So what I'd like to do, my goal here is to educate you on the science of volition and neuroscience, so that if someone comes up to you one day and says, hey, I read this news article that says we don't have free will, that neuroscience has proven that we don't have free will, that you have something intelligent to say about it and understand about it. So there are many different conceptions of free will, philosophical conceptions. They're described mainly with respect to the idea of determinism. So you have incompatibilism, the idea that free will is incompatible with determinism. Compatibilism, which are these notions of free will that are somehow compatible with determinism, and so on. There are too many to talk about now, and that's not really the theme of my talk. I just have these up here as a segue to what I will be talking about. And this is something, among a few things, that neuroscience might have to say that's potentially relevant to free will, which is what I call conscious volition. And the question is, do our conscious willings, right, at least sometimes, have a direct causal relationship with our actions, right? And I just want to clarify briefly, most of our actions, I would submit, are not conscious, right? On an everyday basis, and some clearly aren't. For example, hitting a baseball, we're quite confident that you can't hit a baseball if you wait for conscious information, right? You're swinging before you even know that the ball has left the pitcher's hand, or you will never hit it. But other more mundane things, like you're reading the news in the morning and you reach out to take your next sip of coffee, I think it would be an insult to free will to call that an act of free will, right? But some of our actions are true acts of free will, right? But they're a subset, and I think it's quite fine that many, if not most, of our actions aren't, right? Now, it's important to bring up the reason I mention this is because the feeling of willing and the neural basis of acting seem to be subserved by different structures in the brain and different processes in the brain, right? Most of the time in our everyday lives, they're very tightly coupled. But we can uncouple them, for example, in patients undergoing brain surgery for medical reasons. And in this study, there are actually a couple of studies by a French researcher named Desmarget. He's shown, for example, that stimulation to part of the back of the brain, so the posterior parietal cortex can produce the feeling of a willing. The patient says, suddenly I feel that I want to move my right arm. And then with a slightly stronger stimulation to that same area, the patient will say, I felt like I wanted to move my right arm, and in fact I did, when in fact they didn't move at all. Stimulation to another part of the brain, so the motor cortex, the primary motor cortex, elicited movements without any awareness on the part of the patient that they had moved. So the parts of the brain that directly control movement and that give you the feeling of having willed that movement are different. But again, in everyday life, they're coupled. Now, there's a third area of the brain in prefrontal cortex that it has been stimulated in other studies. And in that case, you get both. You get the feeling of willing and a movement is elicited. Now, this is a rather long quote, but it's worth reading because I think it highlights the topic that I'm getting at today in a very poetic but way that helps you to understand the subject at a gut level. So I'll just read this for you. It's from the book Atonement by Ian McEwan. It's been made into a movie, actually. She raised one hand and flexed its fingers and wondered, as she had sometimes before, how this thing, this machine for gripping, this fleshy spider on the end of her arm, came to be hers entirely at her command. Or did it have some little life of its own? She bent her finger and straightened it. The mystery was in the instant before it moved, the deciding moment between not moving and moving, when her intention took effect. It was like a wave breaking. If she could only find herself at the crest, she thought, she might find the secret of herself, that part of her that was really in charge. She brought her forefinger closer to her face and stared at it, urging it to move. It remained still because she was pretending. She was not entirely serious. And because willing it to move or being about to move it was not the same as actually moving it. And when she did crook it finally, the action seemed to start in the finger itself, not in some part of her mind. When did it know to move? When did she know to move it? There was no catching herself out. Question I've been interested in for several years is this deciding moment between not moving and moving, when one is about to perform a spontaneous voluntary movement. A movement is not provoked by a sensory cue. Now, one of the most important and seminal findings relevant to this question is the discovery of the cortical readiness potential by Kornhuber and Deka, who published this in 1965. I have if you can see the reel-to-reel tape recorder in the background, that's just to highlight the incredible fact that this was how they recorded their data. Right? They didn't have computers or anything of the like, and they actually, at the moment that the person moved, they would then stop the tape and flip them over and play it back in reverse and record it on another tape, and that became their signal that they analyzed. So in this experiment, and which was completely novel at the time, they asked subjects to produce uncued movements at irregular intervals whenever they wanted to. So there was no cue, there was no stimulus. So they would move and maybe wait, and they asked them to wait 15 or so seconds between movements, but not to time it and not to be rhythmic. They needed to leave enough time in between movements in order to capture the necessary EEG data. What they found, and if you see the circle there, 0, that's the moment that they initiated movement, the moment that their muscle began to contract. You see this electrical potential that's slowly building up, starting as much as a second or more before the movement. And this was recorded using electroencephalography over the motor cortex. And you notice it's a bit stronger on one than the other. That's because it's contralateral to the side that they were moving, right? And that's because your right motor cortex controls your left hand and vice versa. Notice also, by the way, that negative is up and positive is down. That's just a convention from the olden days. We tend not to do that anymore. So they decided, Kornhuber and Deka, that this was, and they dubbed it, the electrophysiological sign of planning, preparation, and initiation of volitional acts. Now, this phenomenon actually has its basis, of course, in neural firing, even though we record it using electrodes on the scalp. Depending on how we record it, we give it different names. If you record it using EEG, we call it the readiness potential, or in German, the Bereitschaftspotential. If you record it using magnetic fields or magnetoencephalography, we call it the readiness field. If you record the activity of single neurons, we call it the readiness discharge. It's really the same underlying phenomenon, which I'll refer to as a pre-movement buildup of neural activity. And that pre-movement buildup is not just detectable using EEG, but we can detect it using recordings from single neurons in human patients who are undergoing surgery for epilepsy monitoring. And we see on the right here this same sort of buildup going back a second or more before the initiation of the movement. The same pre-movement buildup has been shown in primates, rodents, and even in the lowly crayfish, which has no cerebral cortex at all, let alone a motor cortex, which interestingly points to a much more evolutionarily ancient mechanism. About 20 years, 30 years after Kornhuber and Deka discovered the readiness potential, Libet, a researcher named Benjamin Libet, did a sort of famous or maybe infamous experiment on it. How many of you have heard of the Libet experiment, by the way? Raise your hand. Some. Okay. Well, so what Libet did, he recorded EEG in the same way as Kornhuber and Deka. He had his subjects do a slightly different task where they had discrete trials. So the trial began, they were watching this clock, which was cycling once every 3 seconds. So that's about 50 milliseconds per tick on the clock. And they were instructed to wait for one full revolution of the clock, and then after that, they could perform the movement whenever they wanted to. Whenever they wanted to. But they were to monitor the clock, and after they performed the movement, they were to report where was that dot on the clock when you first felt the urge to move. Not when you moved, but when you felt the urge to move. Right? The task is difficult and strange and awkward in many ways, which we can discuss over coffee, but the upshot was that subjects were able to do the task, and when you average the data and you average their reports about where the clock was when they felt the urge, you see here that, whoops, I was trying to press the pointer. There we go. When you see here's the time of the urge, it was quite close to the movement. About 200 milliseconds before the movement itself was when subjects estimated themselves to have had the urge. Whereas the readiness potential itself went considerably farther back in time, right? So the inference from that was that, oh, well then, how could we have anything like conscious free will if your brain has already decided to move before you're even aware of your own decision or urge to move? And that view of things held for many decades after that. That became sort of the classical view of the readiness potential, the idea that, whoops, trying to hit the pointer again. Back here, when the readiness potential first is kind of visible above the noise, is when some sort of a decision happened, and then the rest here is just outcome. And somewhere very close to the movement is when the self becomes conscious of the decision or the urge to move. So this is the classical view of the readiness potential, and it's been the prevailing view for many, many years. In the interim, since that paper was published, a number of other papers have been published, some using EEG, others using fMRI, showing the ability, for example, to predict actions well in advance or decisions well in advance of when they happen. An important upshot of those studies about the predicting decisions that most people neglect is that they were only able to do so at slightly better than a random guess, where 50%, right, is a random guess. They were able to classify at about 58% correct, right? That hardly counts in my mind as a prediction, but nonetheless, Libet's study and some of these others, including this one, and this one, which were done in the lab of my dear friend John Dylan Haynes, were cited as further evidence incompatible with conscious free will. Now, since then, I'm kind of jumping forward a bit, but since then, the tides have changed a bit, and I was able to, this is not published, but I was able to get John Dylan to walk back a little bit the way the press, at least, has interpreted his results. And here's his quote: "If you believe that the brain is governed by the laws of nature and that our decisions are realized by our brain, our decisions should not be completely unrelated to brain activity ongoing in the recent past." Right? It would be strange if it were. And this is completely consistent with that. It doesn't mean that we have no conscious free will. It doesn't mean that we've completely predicted your predictions in advance and they were completely determined by your brain activity several seconds before. Nevertheless, in 2016, we have this article in The Atlantic: "There's no such thing as free will." And they went on to cite many of these studies and promote the conclusion that science has disproven free will as a result. A lot of this, again, traces back to Libet's paradox, and that's the topic that I have taken up and challenged in my own research. Libet's paradox is simple: how can purposeful movement causing brain activity begin before the conscious decision to initiate the movement has even emerged? It is a paradox, really, when you think about it. Intuitively and scientifically, here's one possible answer. Maybe the readiness potential is not purposeful and does not reflect the primary cause of movement, right? No one ever thought to ask that question. We discovered the readiness potential and took it and ran with it to the point that we declared free will was dead. Here's an alternate view that I came up with many years ago when I tried to think to myself, what if I wanted to design a robotic arm that could do Libet's task? How would I do that? Because subjects can do the task, so clearly the brain has a mechanism that enables it. Well, there are different ways. One is I could use a random number generator to generate a number of delays and then just implement those one after another. Well, that sounds a little unlike something the brain would actually do. Here's another solution I came up with. What if my actuator, right, to control the robotic arm has some noise in it, and I just kind of push the level of the noise up close to the threshold for initiating a movement of the robotic arm, maybe with a little gentle slope to it so that it's guaranteed sooner or later to cross, right? And then I just wait. And yes, sooner or later, at some moment, it'll cross the threshold and cause the robotic arm to move. And that movement will be spontaneous, even from the point of view of the arm itself, thanks to the noise. Now, this idea is not entirely new. Sir John Eccles, working with Karl Popper, had a similar idea way back when. They said, in a quote here, "There's a tendency for the initiation of the movements to occur during the excitatory phases of the random spontaneous activity. The earlier phase of the readiness potential, up to about 200 milliseconds before movement, would then reflect this spontaneous activity." Right? So I certainly wasn't, and I wasn't the first to think of this idea, but I guess I was the first to seriously entertain it. Libet even mentioned it in some offhand comments in his own papers. So do we have spontaneous fluctuations in neural activity that might enable this sort of mechanism? Absolutely. Neural activity is very noisy, and it's in particular characterized by a certain kind of noise that's called autocorrelated noise, or pink noise. And that's this, so these are both noise here. This is white noise down here. This is autocorrelated noise. And this is the kind of noise that you see in brain activity. Without getting into the complexities of what makes autocorrelated noise what it is, just notice by eye that it's dominated by these slow fluctuations, right? And the faster fluctuations are smaller, right? And the upshot is that if when this reaches a threshold value, for example here, it has to climb up there relatively slowly and in a sort of nonlinear way. So I used this idea to construct a model that could account for the data in Libet's task, the electrophysiology data and the behavioral data, with just two premises. One is that the brain uses the same mechanism for decision-making in Libet's task that it would in any decision-making task, which which is accumulation of evidence to a threshold. This is what neurons and populations of neurons do. They integrate information they integrate incoming impulses over time until they reach a threshold, except that in this case, there's no evidence. There's no sensory evidence. There's no cue. Well, in lieu of a cue, I talk about the imperative to move, which is given by the demand characteristics of the task. Demand characteristics in psychology refer to those aspects of the task that go unsaid, that are just sort of implicit, but they're there. So when a subject comes into my lab and I say, I'm doing this experiment about movement and you're going to press a button every so often, but you can wait as long as you want to press the button, right? Well, in theory, they could wait forever. They could never press the button. They could wait 10 minutes before they press the button. Nobody ever waits more than about 30 seconds because of the demand characteristics of the task. Without me saying it, they know that I'm expecting them to move sooner or later, right? So that takes the place of the signal, right? It's this urge, or not urge, sorry, I shouldn't use that word, imperative to move. The second premise is that when that imperative to move is weak or absent, the precise moment at which the decision threshold is crossed is at least partly, maybe largely determined by spontaneous subthreshold fluctuations in neuronal activity. And those fluctuations appear in the event-locked average as a gradual buildup. If you take many of these crossings and look back in time and see what was leading up to it, you'll recover a gradual ramping, just like the readiness potential. So I turn this into a simple model. This is, for those of you who have some math, this is the differential equation. It's a leaky stochastic accumulator. It's a very simple model. This is the imperative to move, and this is just noise. And this is leak, which amounts to exponential decay in x. It just makes it more biologically plausible that if this thing ramps up and you take away the imperative, it will slowly decay back down to zero, right? When you run the model, it produces traces like these, and at some point they touch this threshold, and what we do is we look first at the distribution of first crossing times of these thresholds, and we find that it fits exceedingly well the distribution of waiting times in Libet's task. That is the distribution of how long people wait before they spontaneously move. If you take these traces here and line them up to the threshold crossing and average them and flip it so that it's negative and consistent with EEG data, you can fit the shape of a real EEG readiness potential exceedingly well. So the model, this model, accounts quite well for both the behavioral and the electrophysiological data in Libet's task. We wanted to test the model, though, by making a prediction. So we did a separate part of the experiment, this interruption experiment, which in the paper I called Libetus interruptus. So the idea is that after doing the regular task for about 20 minutes, we repeat the same task again, but this time we tell the subjects, you might hear an occasional click. And if you hear the click, you should press the button immediately as quickly as you can. Otherwise, just do the task as you were before. You make a spontaneous movement when you want. So they make spontaneous button presses as usual, but if the click is heard, then that interrupts them and they have to move as quickly as possible. The premise here that we're testing is that if this white line here is their threshold for movement, and these are some subthreshold fluctuations going on, if the click just so happens to occur here, then the time that it takes to reach the threshold is relatively short, and so their reaction time should be relatively short. Whereas if the click happens to occur here, then it takes that much longer to ramp up to the threshold quickly, and so the reaction time would be that much longer, right? So the prediction here is that particularly fast reactions to interruptions should be preceded by a buildup in signal amplitude beginning well before the interruption itself, even when the subject was not preparing to move at that particular moment, right? Now, these interruptions were programmed randomly by the computer. They were unknown to me. They were unknown to the subjects. Sometimes they were programmed so late that the subject ended up actually just performing the spontaneous movement, and that was fine too. About half of the trials went that way. But we focused on these interrupted trials. And what you find, I know this is a bit of a noisy figure, but we can just focus here. This is time locked to the click, right? You see that for the fastest third of their reaction times, you have this slow buildup already happening before the click, and you don't have that for their particularly slow reaction times. So it seems that their fast reaction times were fast because the signal just so happened to be that much closer to threshold at the time that the click was delivered, right? And these were the results of the model that the model produced, right? The important thing here, right, to note is that this buildup, in this case, cannot be a preparation for movement because you can't prepare for a movement that you don't know you're going to make, right? There we go. So this leads us to a new perspective on the readiness potential, which is that this early part, this long early tail of the readiness potential is accounted for by spontaneous fluctuations in neural activity, and at a moment relatively close to the time of the movement is when the actual decision, the neural decision to move is made, when the neurons in your motor system commit to executing that movement, right? And this is perhaps a threshold crossing event, and this then is actually, this is not the outcome of a decision anymore, but this is activity leading up to a decision. And importantly, that the time here is about the time that Libet's subjects reported having felt the urge to move. So maybe his mistake was to not have taken his subjects at their word. Now, there's been a lot of support for the model in the intervening years. There's been a number of papers that have come out in support of it. A quote from one of those papers here, Murakami, in 2014, I think sums it up very nicely. Bounded integration models identify the initial intention to act as the moment of threshold crossing while explaining how antecedent subthreshold neural activity can influence an action without implying a decision. Right? So in summary, the stochastic decision model accounts for the electrophysiological, behavioral, and subjective variables in Libet's task. It argues for a late commitment in spontaneous self-initiated movements, and it allows that the conscious intention has a meaningful and reasonably precise relationship with the actual neural decision or the neural commitment to move. It also suggests that a pre-movement buildup might be a general phenomenon in nature rather than a specific mechanism in the brain. Now, one thing that people ask very often, oh, well, does that mean that my movements are just this product of noise? Well, absolutely not. The point here is to account for what happens in Libet's task. And one of the things to note about Libet's task is that you're making a movement for just no particular reason, right? Libet asks his subjects to be spontaneous. So I suspect there's a continuum here. So if you're trying to hit a baseball, right, you don't want spontaneous noise, subthreshold noise in your brain to play much of a role, if any. You want your action to be triggered in response to the baseball. But at the other end of the spectrum, if you're playing t-ball, right, nobody's there telling you ready, set, swing, right? The precise moment at which you swing, then yes, might be slightly influenced by subthreshold fluctuations in neural activity. So by and large, most of our actions on a daily basis, especially where they're in reaction to a stimulus, aren't governed by or caused by or triggered by or precipitated by noise. But in some of them, and in some cases, they are, right? In particular, in a task like Libet's, which was used, I think, and abused and overgeneralized to conclude that there's no conscious free will. So I'll just, in the last few minutes, summarize some more recent work that we've done along these lines. So one thing is, if you wanted to study what happens before a spontaneous voluntary movement, what you would do ideally is have some data epochs without a movement and some epochs with a movement and compare them. But we never have that in the field because with a spontaneous movement, we don't know what to look at in the data unless there's a movement. So when there's a movement, we time lock to the onset of the movement and look at what's happening before. So there are no epochs without movement. So we wanted to try and find a way around this problem. This is work that I've done with Rob Shapire, formerly at Princeton University, now working for Microsoft Research, and his then graduate student Mehmet Basbug, and now my PhD student Luca G. This was using magnetoencephalography and electroencephalography data recorded simultaneously. What we had was a very simple paradigm where subjects looked at pretty pictures of nature. They could advance the slide when they wanted to, but there were two different conditions. On the manual condition, the subject knew that they would look at the picture for as long as it pleased them and then move their finger to advance. For the trials preceded by the word automatic or auto, the subject knew that they just waited passively and the slide would change by itself. But what we did was we drew the viewing times for the automatic trials from the subject's own waiting times on their manual trials. So that by the end of the experiment, we had these two conditions that were relatively well matched in terms of anticipation. And then we did, so now we have these movement plus slide transition and these slide transition only trials. So this has movement here, no movement, and they're aligned to the slide transition, right? So we did some machine learning analyses on these data in a sliding window. I don't know if I can, with this, make this work. Let's see, no. Okay, well, never mind. We'll just jump to that. We did some machine learning analyses in a sliding window to see at each point in time of the window, could we tell these two apart, right? Now, if the readiness potential is any indication, we should be able to tell them apart maybe a whole second in advance. But this shows a very different picture. 50% here is just a coin toss. This is just a random guess. And this is for our first three subjects. And you see that we can't tell them apart at all until very close to the time of the movement itself. And then at that moment, we can tell them apart exceedingly well. This is a very powerful machine learning technique. So it's not that the machine learning algorithm, which is something called AdaBoost, it's not that it wasn't working, right? It's clearly working. But these are relatively indistinguishable before about 150 or 200 milliseconds before the movement. Right? And this is what the readiness potential looked like. It stretches back a full 2 seconds before the movement. Right? So this demonstrates that this electrical potential, this pre-movement buildup that looks like it's causal with respect to the movement and predictive of the movement, well, it maybe isn't. Sorry? Almost 2 seconds before. It's highly variable. That's another puzzle with the readiness potential. In some subjects, it goes back 500 milliseconds, a second and a half, 2 seconds. It's incredibly variable. So that also raises another question, right? Which is, why would nature set something up where your brain makes a decision and then waits like 2 seconds to actually carry it out? So another study we're doing is looking at what I call the metaphysics of spontaneity. We're also using machine learning to do this. You might think in this context, here's a football player and he's about to cut left or cut right to try and outwit his opponent. And well, if he does a movement and he succeeds in outwitting his opponent, is it spontaneous, right? Well, from this perspective it is, but if I could look at his brain activity, maybe all would be laid bare, right? Maybe it's a subset of his brain activity, so if I looked at some of his brain activity, it wouldn't, but if I looked at a certain subset, all would be laid bare. Or, pushing it even further, maybe it's just spontaneous. Maybe we make use of our own neural noise in order to be random in a way that is advantageous sometimes, right? And this is something that's come up in game theory, in fact. So these are the two possibilities, right? You decide well in advance and then act, or decide at the very last moment. We instruct our subjects on each trial. They're instructed to move left or move right, or to decide now, or to just wait until the very last moment and be spontaneous. Libet would predict that we'd be equally good at classifying those at all of these, right? Even when you feel like you're spontaneous, your brain's already made its decision in advance. But that's not what we find. When we look at the earliest decoding time, you see that it's quite early for the instructed and early conditions, but for the spontaneous ones, we can only tell them apart towards the time of the movement. So future directions that we're taking up now is looking at the prediction of movement more like we would look at forecasting the weather, rather than looking at, which the readiness potential does, the probability of the signal given a movement at time 0. We want to look at the probability of a movement in the future given the signal now. And that produces maps that look like these, and they can actually, the shape of this distribution looks different for something that's stochastic versus deterministic. And we can use that across all different spatial scales and in different animals. We're collaborating with a research group in Chicago that allows us to do this with mice. So postscript, I just want to leave you with this. Neuroscience certainly has not provided any evidence that's patently inconsistent with conscious free will, in my opinion. But what would count as evidence against conscious volition if it were to ever come to pass, right? Well, if you could consistently predict action well in advance, several seconds or more, based only on brain activity, with very high accuracy, around 99%, allowing a tiny bit for measurement error, then we'd have something to at least have a conversation about. No one's even come close to that, and there's good reason to believe that they won't, right? And I'll leave you with this. A single human brain is arguably far more complex than the entire Earth's atmosphere, for reasons that we can chat about over coffee. And look at how good we are at predicting the weather, right? It depends on where you are, of course, but I sincerely doubt that we'll ever be able to achieve that in a system as complex as the brain. Thank you.
Thank you very much. It was a very interesting lecture. I'm sure there are many questions and comments.
I'm inspired by your last sentence because the weather is, as far as I know, the chaotic system, deterministic chaos. Yeah. So in principle, it is deterministic. All the laws that govern the air is deterministic, but we cannot predict far enough in the future because of this chaotic nature. Do you think this could be the case with the brain, or maybe some other effects take place here?
Well, I mean, I'm not a physicist, but insofar as quantum effects matter to neural activity, which is conceivable, then it may not be deterministic chaos, right? It might be indeterministic. But yes, I would say that the brain is that sort of system. And it's governed, well, and we talk in the field, we talk about criticality, that the brain operates at the point of criticality, which is a sort of very delicate point on the edge, right, of chaos. And that enables it to be more agile.
There was a question over there.
Thanks, first of all, for a very informative, great talk, very clear. The field is new to me in many respects, although extremely interesting. Now, earlier in your talk, you made a distinction between, or at least you mentioned, that we might be influenced, or that our actions of what we consider free will might be determined by this build-up that is eventually reaching the stage at which we consciously make a decision. Now, being influenced, being determined is not exactly the same as being influenced. You might be influenced, but not determined to do things, right?
Right.
That's a very important distinction. Of course, I understand it, if I understand it correctly, that in your presentation, you presented a somewhat simplified picture for the purpose of explaining the Lipid experiment and also how to falsify it, how to respond to it. Now, let me give you an example from my own experience, and it's a very common experience. I sit and work, and at some point I sort of think, oh, it's maybe time to eat something, right? at that moment, or soon right after that, I started feeling a bit hungry. Right? Now, my question is the following to myself. Because I looked at the watch and I started saying, oh, this is my time to eat, then I started feeling hungry. Sort of that influenced the circulation of blood in the brain, in the stomach, or some signals there and back. Or maybe was it that the stomach was sending signals to the brain saying time to eat, and I was not realizing it until it got to the stage at which I realized, oh,
no.
It's something I need to do. Why? Oh, because it's time to eat. So there are two different interpretations of the same thing, perhaps. I mean, two different possibilities, I would say. Which one do you think is more closer to reality, to what actually happens? But before I let you answer, I think that even if once we realize that we are hungry, even then we can make a conscious decision to eat or not to eat. So that's, to me, an example of having free will to decide what to do with the impulse that I receive to my brain, one way or another.
So I'll say this. It could be very well a combination of both. Perhaps looking at your watch primes, right, hunger that was latent, or it could be the latter. I would tend to lean towards the latter. The ideas that I'm talking about here do not deny the possibility of pre-conscious or unconscious effects. I study these myself. They're very real. There's a very nice experiment by Antoine Bechara from way back, where you have two decks of cards and you don't know anything about these two decks of cards, and you're drawing from them, and you have to, one deck is advantageous, it has better cards than the other, and you start drawing from the decks, and you just have to learn through trial and error which is the better deck. Well, and then you're instructed to say, once you know which deck it is, you have to say, I know now which it is. Well, you start to favor one deck over the other long before you know which deck you prefer. That's just one example of that kind of study. So these kind of pre-conscious effects are very real. I mean, if your conscious decisions and your conscious perceptions come from your brain, are generated in your brain, then it stands to reason that the antecedents are in your brain as well.
Good. Thank you.
A quick question? Okay. Final quick question.
Oh, so there is a specific version of this lipid paradox you cited, which is focused on lateral readiness potential, that like in right-left-hand tasks, this lateralization, the difference between RPs precedes the urge to move. Mm-hmm. Does this stochastic model also predicts this early lateralization, or is it unrelated?
The model as is doesn't, because the model only models the decision of when to move, whereas the lateralization involves a decision of which hand to move, or you're instructed at least to move one. So the model is just like a one-handed model. You could extend it, and there are models of the lateralized readiness potential. It becomes apparent in the EEG signal much later, as early as 400 milliseconds, but usually or more around 200 milliseconds before the action. The signal becomes lateralized between the two hemispheres, indicating which hand you're using.
Like, just quick follow-up, so like this line of like Libet's like classical line of thought that like something happens in brain before the conscious willing with respect to lateralization. Like, how is it? Like, what's the how sound is the argument that we can already, like, the brain already decided because like one hemisphere is more active, one like half second before?
Well, it's for the lateralization, it's not a half a second. Maybe it's at most 400 milliseconds, usually around 200 milliseconds. I don't think that's evidence that the brain has already decided, because your feeling of deciding comes pretty close in time to that as well. So.
Let us thank the speaker again.
Thank you.